Hey, welcome back. In this lesson, we're going to talk about the dot product. In this lesson and the next one, you'll learn about two ways to combine vectors that are like multiplication. In this one, we'll learn about the dot product, and in the next one, we'll learn about the cross product. Both of them are super useful when it comes to doing things with vector geometry, but they are different in some pretty big ways. So in this video, we'll talk about the dot product, like how to compute it, what it means, how to interpret it, and in the next one, we'll talk about the cross product. Here we go. So let's start with the definition of the dot product. In other words, how do we compute it? If we have two vectors u and v and their components are u1, u2, u3, v1, v2, and v3, then the dot product of u and v is going to be an operation that we write like this. We're going to write u, a big old dot, v. And the way we compute it is we take the x coordinates of u and v, so u1 and v1, we multiply them. And then we'll do the same thing with the y components, so we'll do u2 times v2, and we'll add them. And then we'll do the same thing with the z components. So we're just multiplying corresponding components and then adding them all together. For what it's worth, the way we read this is u dot v, usually. You could also just say the dot product of u and v. And the thing that I want you to notice off the bat is that since u1, u2, u3, and v1, v2, v3 are numbers, right? They're real numbers. We're taking them, multiplying them, and adding them together. The result that we're going to get is a number. But in our vector parlance, we're calling those scalars. So it's the dot product of two vectors is always a scalar. So we take dot products of three-dimensional vectors like this. The way to take the dot product of two-dimensional vectors is pretty much the same. So I'll just write that here. For vectors in R2, for instance, if you had A1 and A2, and you were taking the dot product of that with B1, B2, then you do the same thing. You'd multiply corresponding components and add them together. And it turns out that pretty much anything that is true about the dot product of two three-dimensional vectors is also true about the dot product of two-dimensional vectors. So for the rest of this video, I'm probably going to refer to two and three-dimensional vectors interchangeably because they work with the dot product in the exact same way. Okay, so something you might be wondering right now is, what's the point? Why are we taking two vectors and combining them in this kind of non-obvious way? Like, why aren't we just like multiplying component-wise? Well, it turns out that this algebraic way to combine vectors by like multiplying corresponding components and adding them actually has a connection to the geometry of the vectors involved. And I'm not going to get into the details of all of that here, but I do want to write down like pretty much the two big dot product facts that we use to connect the dot product as an operation to the geometry of the vectors involved. So the first so-called dot product fact comes from looking at what happens when you take the dot product of a vector with itself. So if u is this same vector up here, u1, u2, u3, and we look at the dot product of u with itself, well, okay, just from the formula for the dot product, that should be u1 times u1 plus u2 times u2 plus u3 times u3. Another way you could write that is u1 squared plus u2 squared plus u3 squared. And so looking at this off to the side, this is almost the formula for the length of u, for the magnitude of u. All it's missing is the square root. So what that means is when we take the dot product of a vector with itself, we get its magnitude or length, but squared. It's missing the square root. So this little observation is actually sort of the bridge to a like larger understanding of how the dot product works. It's a connection between this algebraic formula for combining two vectors to get a number and the geometry. Like this is the length of the vector. So it's connecting an algebraic thing to distance in R3 or R2. The second dot product fact is actually probably the most useful thing about the dot product. It's sometimes called the angle formula, but it goes like this. If you take the dot product of two vectors u and v, then that is equal to the product of the magnitude of u, the magnitude of v, and the cosine of the angle between the two vectors. And what this means is if u and v are any vectors, either two-dimensional or three-dimensional, then remember that vectors are only directions and magnitudes. It doesn't matter where in space we draw them. So we can draw them with their tails being at the same point so that they kind of make a letter V shape like this. And so the angle theta is the angle between them when they're drawn like this. So this formula here is infinitely useful. Like I said, sometimes it's called the angle formula for the dot product. But I actually like to think of this as this is another way to define the dot product. And it's sort of a complementary definition to the one that we started with, in the sense that if you had two vectors and you could compute their lengths and you somehow could find the angle between them, then this formula is telling you what the dot product should be. So it's another way to define the dot product, but instead of using the components of the vectors, it's using the geometric relationship between them. So I'll summarize that by saying that this first way that we define the dot product, this is useful for computing the dot product. Whereas the angle formula, this is useful when you're using the dot product to sort of do geometry, to like understand geometric relationships between vectors. And lastly, I'll note that if you're wondering where this came from, because I didn't justify this. I justified the first one with this kind of like little gray side computation here, but I haven't told you why this is true. And I'm actually going to leave that to you if you want to really get into it. On the worksheet for this class, there will be a problem at the end where you can go through the derivation. It uses this fact about the relationship between the dot product of a vector with itself and distance, and it uses the law of cosines, which sort of kind of like explains why the cosine is showing up here. So if you're interested, you can go check that out after this upcoming class. So that leads us to what I'm going to call the interpretation of the dot product. And the way I like to say it is the dot product of two vectors u and v, it tells us how much u and v are pointing in the same direction. And this interpretation, it all comes from the angle formula, which I'll write here again. And what I mean by that is there are sort of three cases to look at for the dot product of two vectors. The first is if the dot product of two vectors is positive. So if the dot product of u and v is a positive number, then going over to the angle formula, we have a positive number on the left. The magnitudes of u and v are always positive. And so it tells us that the cosine of the angle between them is a positive number. And so bringing in a little bit of knowledge about the cosine function tells us that the angle is a number between 0 and pi over 2. So if the angle is 0, it's saying that the vectors are pointing in the exact same direction. In other words, they're parallel. And if the angle is anything between 0 and pi over 2, then that's an acute angle. So the next case is the opposite of that. If the dot product of u and v is a negative number, then, okay, well, if the cosine of an angle is negative, it means that the angle is something bigger than pi over 2 and less than pi, which is 180 degrees. And so the picture to have in mind is one where the angle between these two vectors is bigger than 90 degrees, bigger than pi over 2. In other words, it is obtuse. And lastly, and this is probably the most important one, if the dot product of two vectors is exactly equal to 0, then we know that the angle between them, because cosine of theta is 0, we know the angle between them is exactly pi over 2. And that means that u and v meet at a right angle. So I'm highlighting this last line here because it's probably one of the more important facts from this lesson. Again, if two vectors have a dot product of 0, it means that the angle between them is 90 degrees. And a way to say that differently is that the two vectors are perpendicular. And this ends up being a really useful fact, especially when it comes to describing planes in three-dimensional space. You'll see that when we're trying to come up with the equation for a plane, we want to identify certain vectors that are perpendicular. And so the dot product gives us a way to do that. And again, I'll point to the top here and just reiterate that if you want to understand what the dot product of two vectors is telling you, it's answering this question. It's answering how much do u and v point in the same direction, in the sense that if the dot product is positive, then the vectors sort of point in the same direction. The angle between them is obtuse. If the dot product is negative, then the vectors sort of point in the opposite direction. In other words, the angle between them is obtuse. And lastly, if the dot product is 0, then they are perpendicular. Okay, so the last thing I want to tell you about in this lesson is sort of related to that interpretation of the dot product as the degree to which two vectors point in the same direction. It's called the scalar component. And I want to mention it here because it comes up just every once in a while when we're doing vector geometry. So the scalar component of one vector in the direction of another, it answers the following question. How much does the first vector, u, point in the direction of the second vector, v? Now, this is very similar to the interpretation of the dot product that I wrote down earlier, except it is sort of asymmetric. It's asking how much does one vector point in the direction of the other. So to answer this question geometrically, let's draw the two vectors. Let's say that v is this green vector and u is this orange one. And so the way that we're going to answer this question, how much does u point in the direction of v, is by thinking about, in this picture, like what is the amount that this orange arrow points in the direction of this green arrow? And the way that we measure that is with a distance. By drawing a little dotted line from the tip of u that hits the vector v at a right angle. And so the way that we'll answer this question is by trying to figure out what this distance is, because it's sort of the degree to which this orange vector is pointing in the direction of the green vector. In other words, we're kind of combining these two vectors, taking the direction of the green vector and the length of the orange vector. So if we wanted to actually compute this, let's give this a name. Let's call it just x. And let's try to figure out what x is. Now, since this is the lesson on dot products, it makes sense that we're going to use the dot product to figure out this length x. And again, we'll be using that angle formula. So if we draw in the angle theta here between u and v and write down the angle formula, and now using a little bit of trigonometry, let's try to figure out what this length x is. We have a right triangle with an angle theta. The side adjacent to theta of this right triangle here has length x. And the hypotenuse has length whatever the length of u is. So we get a second equation that is the cosine of this angle is also equal to x, which is what we're trying to find, over the magnitude of u. So to figure out what this scalar component is, we want to solve these two formulas for x. From the second one, we get x is the magnitude of u times the cosine of theta. And plugging this cosine of theta into here, we get u dot v on top. And then this magnitude of u in the denominator cancels with this magnitude of u here. And so we're just left with u dot v over the magnitude of v. So that little algebraic step was just to compute this length. And again, the point was kind of to answer this question, how much does u point in the direction of v? Now we have a way to quantify that. Again, it's called the scalar component, and the way we write it is COMP. We put v, the vector that we were looking at the direction of, as a subscript, and then u here not as a subscript. And again, it's equal to the dot product of these two vectors divided by the magnitude of v, the vector that we were looking at the direction of. So, okay, again, I'm including this in the video just because it'll come up at some point. You'll probably have a couple practice problems to do with scalar components. This sentence here, how much does one vector point in the direction of the other, is really the geometric interpretation of it. And all of this algebra here was just to compute it. We get this formula. And again, you'll see more about why this is useful as we move forward. That's going to do it for this lesson. The dot product is going to become something that we use pretty much all of the time when we're working with vectors, because it is a way to connect the algebraic side of vectors, like knowing about their components, with the geometric side. In particular, as we saw, the angle between them and like how much two vectors point in the same direction. Sometime between now and when we see each other in a video again, you'll figure out how to use the dot product to come up with equations for planes, which is super useful and has a lot of applications throughout all of calculus. But until then, thanks for playing along, and I'll see you later.